we studied about CFT, we studied about CFSE. Now we are going to study about complexes being colored. Now color of complexes are owing to two reasons. One is DD transition and another is charge transfer. Alright, we are going to study about these two significant properties owing to which metal complexes get color. Now just let's recap of what we had already studied. The example that I have chosen over here is titanium hexahydrate. Now titanium, water we know is neutral, it doesn't have any charge. So if the complex has 3+ charge, then that itself is owned by titanium. So it is titanium 3+. And when it is titanium 3+, so it has lost 3 electrons. So 4s2 is gone. So it is 4s0. And from 3d2, 1 electron is gone. So it is 3d1. So the configuration is Ar argon configuration along with 3d1. What we are concerned is with 3d1. We are concerned with d orbital. So 1 electron which is there is suitably placed here. So we know it is dx square, y square, dz square, dxy, dyz and dzx. So electron, all of these d orbitals are at equivalent energy. So I place it over here. Assume that 6 ligands are approaching towards central metal atom, that is titanium, towards Ti3+ ion. Alright. If we are talking about 6 ligands approaching towards the central metal atom via x, y and z axes, then obviously we are referring to octahedral complex. Alright, so yeah, so 6 water molecules approaching Ti3+. So this is how this splitting. Now it is approaching, just approaching, approached, approaching very close, and it has approached to its suitable position. Alright, so we are finding that the energy level between T2G, EG keeps on increasing as the ligands, water ligands approach central metal ion, titanium. Alright, so this is ultimate splitting. So now T2G and EG, the difference, energy difference is delta O. Alright. Now let's understand, it has got this situation. So now let's come to this part. Okay, now let's assume that visible rays of light falls on titanium hexahydrate complex. Alright. It falls in forms of photon, light packet, h nu. H nu we know is equal to hc over lambda. H is Planck's constant. C is again velocity of light. It's also a constant. So it depends on lambda. So lambda is the wavelength. And we know energy is inversely proportional to lambda. Alright. Now this complex picks up the desired wavelength from Vibgyor or Vibgyor, whatever you call it. And what happens is it desired wavelength. What do I mean by desired wavelength? Desired wavelength means the wavelength that has the energy capacity, that has the capacity to make this electron jump from T2G to EG level. Alright. So this electron picks up, and here we are finding that the electron has picked up the desired wavelength of desired energy and is jumping from T2G to EG level, and here it has jumped. Alright, so while doing so, it has picked up one wavelength of desired energy for letting it jump from here to here. Now the complementary colors, so wavelength in visible region, so it corresponds to a particular color, so that color has been absorbed for jumping, but the complementary colors, that is the colors which remains behind, are transmitted back, and when those colors are transmitted back, what color do we see? We see purple color. So this is the reason why we find titanium hexahydrate 3 plus purple in color. This is the entire process that happens during approach of ligand to metal and for the complexes to appear colored. Alright. Alright, now there has to be certain criteria for the complexes to be colored. Now, because all the complexes are not colored, all the metal complexes are not colored. So what could be the criteria for metal complexes to be colored? Let's try and understand. Now, just to take an example, if we observe zinc. Now, in case of zinc complexes, Zn2 plus complex if we observe. Now, Zn2 plus complex has, if I take Zn0 configuration, it would be argon. It would be Ar 4s2 3d10. To form Zn2 plus, it has to give out 4s2 electrons. So what is left is argon and 3d10 as configuration. Now if it is 3d10 is the configuration, then in that case all the 5d subshells are filled with electrons. There is no empty space, empty d subshell for the electrons to jump. Alright, so how do we expect color? So there won't be any absorption of wavelength from visible region for jumping, so it won't be colored. Now coming to scandium again, which is 3d1 4s2. For forming scandium 3 plus, it has to strip 3 electrons. So as a result of which 4s2 gone and 3d1 gone. So the configuration is 3d0. Now if it is 3d0, then there is no electron left to jump. No electron left to jump from T2G to EG if we are talking in terms of octahedral complexes. Alright, so first criteria that we understand for the metal complex to be colored is D subshell has to be partly filled. Alright, so if it is not partly filled, then there won't be color. If it is fully filled or if it is empty, there won't be color observed for the complexes. Alright, that is one thing. Then we also come to oxidation state of metal. That also is responsible for color of the complex. Then it also depends upon ligands to which metals are attached. So oxidation state, ligands to which metals are attached, and also partly filled d orbitals are the criteria for metal complex to be colored. And now we call this as DD transition. Why? Because we saw that the transition was from T2G of D to EG of D. So we call it as DD transition. Now let's understand charge transfer. Color owing to charge transfer. Now this color occurs owing to fractional shift of electron density caused by electronegativities differences or orbital configuration rearrangement. Alright, so charge transfer, this happens, obviously we can expect it to happen because of electron density. Now suppose there is some, now when we have got a metal complex, now we are talking in terms of octahedral, so I have shown 6 ligands here. Now we are now charge transfer occurs via 2 means. One is LMCT, that is ligand to metal ion charge transfer, and the other one is MLCT, metal ion to ligand charge transfer. Now I've just tried to depict here both the situations. Now this is metal and these are 6 ligands. Now since speaking about octahedral complexes, so I have chosen 6 ligands here. Now when we are talking in terms of ligand to metal, now I have shown here these are the charges which are being shifted towards metal. Alright, so this is ligand to metal charge transfer. Whereas here what we find is other way around. It is metal to ligand. It's our guess anyways that when electronegativity of metal is more, it would be this occurring. And when electronegativities of ligands are more, then the charge would be moving towards ligand. So the charge would be transferred towards ligand. Alright. Another thing that is important to know about this is that this requires much higher energy than DT transitions. So what we saw is DT transitions and charge transfer. Alright. Now these are the two causes owing to which the complexes show color. Obviously, now here we are not talking in terms of DT transition, but I just wanted to express charge transfer also a cause for color of complexes. Alright, so guys, I am putting all my effort to make things clear to you all. So please do put in your effort in understanding and studying well.